In this lecture, we are going to talk about expanded octets. I feel like we have developed a pattern here where give you some handy rules to follow, and then I follow it up a little bit later with saying, well, but now here's all the exceptions to that rule. This seems to be a pattern in chemistry when you're learning it initially. So sorry, but this is kind of interesting. So the octet rule is really handy for figuring out what structures will form, and especially for a lot of organic compounds that are primarily carbon, oxygen, and hydrogen, it works great. But we have a lot of elements that can expand their octet in a sense. And so they'll create sometimes molecules in nature that don't fit this octet rule style of prediction. But there's a great explanation for why it happens, and it's easy to predict. Um, so so some of the exceptions, let's start with the easy ones. First of all, odd number electron species. So things like nitrogen, oxygen bonded together. These are typically going to have one unpaired electron, and they will be a free radical. They are super reactive. And if you're interested in kind of the reactivity of free radicals, there is a wealth of information about it out there about how free radicals act in your body. And you have all these like systems to help prevent damage by free radicals because they'll just like start reacting with DNA and stuff like that. But also free radicals play a really huge role in our atmospheric chemistry as well. And so things get really interesting there too. And oxygen is a lot of times one of the culprits in these free radical chemistry style situations. Anyway, so one exception to the octet rule is that some compounds are free radicals. They have one unpaired electron. They're super reactive. And so one of the atoms on the Lewis structure will not have a full octet. I will say, please create a Lewis dot structure that has a free radical or one unpaired electron if I want you to do this. So always assume that you're going to use the octet rule. Now, we have some examples that are incomplete octets. And the examples are boron and aluminum. Now, boron is only going to form a 6 electron structure. Aluminum is similar. And what's happening here is this is in the third group of the periodic table. And boron is a metalloid, so it's already kind of weird, right? And so with this exception, we would think of boron as having 3 electrons to start with, valence electrons. And when it fills around, let's say it forms a bond with hydrogen, it's only going to fill up to 6. Isn't that weird? And so this is when you just kind of need to remember that when you're working with boron, it's weird and it only wants 6 electrons. So these are our less common exceptions to the octet rule. Now, the very common one is expanded octets, and we see a lot of this. And here's an expanded octet means there'll be more than 8 valence electrons around an element. Here's an example right here. Sulfuric acid. The sulfur has a 12 electrons around it. It's got 6 bonds, and each bond has 2. So it's experiencing 12 valence or 12 electrons around it at that time, which breaks the octet rule. Now, the oxygen and hydrogen are following their rules just fine. But why does sulfur do something different? Okay, it's about its position on the periodic table. And so in the periodic table, elements that have empty d orbitals are going to be able to have more than 8 electrons. And what they're doing is they're putting those extra electrons in the empty d orbitals when they're forming these bonds. That's where they're overlapping. So anything in the third row or lower on the periodic table can do this. So if you imagine our periodic table, that's not a good periodic table. Here we go, better periodic table. Everything in the third row. So all of these elements right here can expand their octet. And when we're talking about covalent bonding, we're really thinking about these ones right here on the non-metal side. And so remember, when we were talking about electronic structure, those 3D orbitals are pretty high, or those 4D. So if I am something in the third row and I have like my s electrons filled, so let's call this 3s, and I have some, let's say a couple 3p electrons, so this would be for sulfur. Then there's the 4s electrons, and then there's the 3d electrons. So this is the electron configuration orbital diagram for sulfur. And so these are the electrons in my valence shell in the 3s. So these are my valence electrons that are going to participate in covalent bonds. But in that same shell, right, that same energy level for principal quantum number n, we have all of these empty 3d orbitals in that same energy level. Even though it's at a higher energy than our p orbitals or our s orbitals, they're available. And so expanding the octet means using these d orbitals. And we'll get into a much clearer picture of this in chapter 8 when we talk about valence bond theory and hybridization of orbitals. But for now, we can just say, here's this really cool thing. They can expand their octet, which really opens them up to different geometries, and it's really fascinating. And so if you have something in the third row or below, you don't have to obey the octet rule.